Now let us take this wonderful question on hydrogen spectrum, or you can say hydrogen-like spectrum. Let's read the question very carefully first. The question wants this quantum number n corresponding to some excited state of helium plus if it transition is happening to the ground state, but that is coming in two forms, like 108.5 nanometer it is emitting, and then it is emitting 30.4. So like let's picturize this. So it starts from this point n, and it's like have a little pause at k and then comes to the ground state. So obviously we are not interested in this k anymore. We are interested only in finding the value of n. So what would be the immediate thing would be, when this helium plus sample directly comes from n to 1, this would be the lambda emitted. So from the conservation of energy, we can apply this logic. 1 upon lambda would be equal to 1 upon 108.5. Actually, I'm using the photon energy formula. Hc has been cancelled out. So remember the background. Energy is equal to Hc by lambda. So lambda would be equal to Hc by energy. So here I'm conserving energy now. So let's say you get to this lambda, but make sure this lambda is for the helium. So what I would request students to remember is that, suppose we get this lambda, let's say we get this lambda, then we transform this lambda into the corresponding transition that would have taken place had this been a hydrogen atom. So when I say corresponding transition, the orbits I have to keep the same from n to 1. And you would note one thing, that helium plus has the proton count equal to 2 and hydrogen has proton count equal to 1. Since energy of hydrogen would be definitely, like magnitude wise, less, z square less than the energy of helium. So I would say, if this is the lambda for helium plus transition, what would be the lambda for hydrogen transition? It will be 4 lambda. Now you know interesting situation in hydrogen. If you exactly come from the infinite orbit to the ground state, then it's like an ionization energy data we have. So please remember, from the Rydberg constant we can calculate this to be 91.1 nanometers. Now you just figure out how this 4 lambda is coming out. So what you can do is write this 1 upon 4 lambda would be equal to 1 upon 91.1 multiplied by 1 upon 1 square minus 1 upon n square. And then you can keep substituting the value of n to figure out the value of this particular n. So it will be few hit and trial. So try with n equal to like 2, 3, 4, 5, or any number you can think of. Obviously k you don't have to find, so you start from 3, 4, 5 like that and proceed further.